Hi everyone, welcome back to another workshop by Neurotech at Davis. Today we'll be covering machine learning basics, so let's get started. Here's the outline of what we'll be going through today. So we're going to skip the recap of last week. We do have another tutorial posted about signal processing if you're interested, so you can check that out. So let's start with what machine learning is, how we see it in our day-to-day lives, what types of things can be used to predict. We'll go over how it's relevant to brain frequencies, BCI creation, really related to a neurotech context, binary and multi-class classification, and their commonly used models. And then we already have an interactive coding demo up with some of the models that we created on this YouTube channel. So feel free to check those out. Okay, so let's get into what machine learning is. So it's a way to predict different things. So some common examples from this video are things like autocomplete text, which you might see on iMessage when it suggests what words to use next, or on email when they try to finish whatever sentences you were saying. So those are examples of how it's used for autocomplete. There's things like email filters that can detect whether an email is spam or not and automatically filter it. Video recommendations, so on YouTube, Netflix, things like that, where it will automatically suggest to you what to watch based on what you've watched in the past or what similar people to you are watching. Digital assistants like Google Assistant and Alexa and things like that, as well as like voice recognition, to unlock things, or for whatever it may be, translation apps like Google Translate. So all of these are using machine learning. It's just a way to emphasize how involved it is in our day-to-day lives, whether we realize it or not, and how it's becoming increasingly more present. So it's good to know what it is, at least to a basic extent. And then I want to bring this up to show how machine learning can be used to predict a variety of different things. So you can start with images, maybe predicting what something is, or video, same thing, like figuring out what something is. And there's just a variety of things that the machine learning algorithms can detect from the content that you feed it. Audio, so it can predict things with signals like audio, brain signals, things like that, as well as text. So we've seen a lot of text examples in the previous picture. Okay, so now that we have a basic kind of overview, let's talk about, let's talk about two different types of machine learning. So supervised machine learning is when you label the data and feed it in, and it uses that to make predictions. So for example, let's say I feed in these apples and I annotate them saying that these are apples. When I feed in another apple, it'll be able to use this labeled data to predict that it is an apple indeed. So similarly, if I fed in a bunch of different fruits with labels saying what they were, and then I fed in another fruit, it would be able to tell me, oh, it's one of these or it's none of these. So that's what a model can do when you feed it labeled data. There's also unsupervised learning. So here we can see we fed in apples, bananas, peaches, and we feed it into the model. And instead of telling us what it is because it doesn't know, it is able to just group it together and make a prediction about which belong together. So we can see that it grouped the apples together based on similar characteristics, same thing with the peaches and the bananas. So yeah, that's a basic example of supervised and unsupervised learning, and they're used in a lot of different contexts. So mostly for like company data and stuff like that, you'll have supervised learning because it will be labeled data. For things where you're just trying to predict patterns, or you have a bunch of data and you want to see if you can get any information from that, you might try unsupervised learning. So they're just different techniques that people use. And then there's another cool video that you can check out in your own time called Signal Processing Using Machine Learning. It has some good examples of how machine learning is used for signal processing, and it covers a BCI example as well. So I definitely recommend that you check this out. Okay, so now let's get into really quick how machine learning would look with a BCI architecture. So first, it would start right here. You would start with EEG signal acquisitions, and if you watched the last video or one of the previous videos, you know how we acquired signals from the brain. You do the electrode placement and you get the signals, and you would pre-process the data, feature extraction, classification, translation into a command, and feedback. So an example of this is a project that we made last year, which would be when we collected the EEG data to detect eye signals. So our pre-processing was to clean up the data and then also to train it in the model with what the different eye movements were. So blinking, looking side to side, looking up and down, keeping it stationary. Feature extraction was to separate out those things. And then classification would be to identify which one we would be doing. Translation into a command would be something like turning on a light bulb, which is what we did. Okay. Binary classification. Now, binary classification just means classifying the elements of a set of data that you get into two groups on the basis of a classification rule. So some real world examples of this would be like email classification, like we talked about before, when the model can detect whether it's spam or not spam. We could use it in a medical setting where we could detect whether certain scans look cancerous or not cancerous. Eye movement classification like we did, whether someone's in a blinking or rest state. So let's go into some commonly used models. So first is logistic regression. So the basic idea of this is that it predicts conditional probability. So for example, if we're modeling people's sex as male or from their height. And the first class could be male, and the logistic regression model could be written as the probability of a male at a person's height, or probability of sex equals male given height. So it's predicting one value based on what you're given. So here you can see what the back end of the model looks like and what it'll be shown visually as, but if it falls into this blue space, we'll predict that it's a blue thing, whether that be like male or female or something of that sort, some binary classification, spam or not, cancer or not, something like that. And so you can see where there's a couple of spaces where the blue dots fall in the orange area, so those would be incorrectly classified, but that's the basic idea of it. And then the next one we'll go into is K nearest neighbors. So what this essentially tries to do is it determines where a data point belongs to based on the data points around it. So what the K number does is how many nearest neighbors it'll look at. So for K equals 1, it looks at this red dot, that's the one we're looking at, right? And it looks at itself because that's its nearest neighbor, and it'll classify on that. But that creates kind of an uneven boundary where it's isolating that one red dot, which is, yes, very accurate, but not the most ideal case scenario. So instead, we'll look at K equals 3. So this red dot will look at the three neighbors nearest to it, and based on that, we'll decide a decision boundary. So here we're looking at these two dots, maybe this one, and since they're blue, this all falls into the blue category. And as you increase this K, it'll be a more stable prediction. And so obviously there's going to be a few misclassifications, but the goal is to accurately classify as many points as you can. Okay, and then let's go into one more, which is support vector machines. So the objective of this is to find a hyperplane in an n-dimensional space where n is the number of features that distinctly classifies the data point. So if you see here, it's this n-dimensional space where you can kind of see there is a separation that wouldn't be shown on like a 2D plane, but it's kind of like there are some yellow dots up here and some red dots at the bottom. So if you had a hyperplane cutting straight through, you'd be able to separate those two classifications. So similarly, we have another example right here, which is just shown on a 2D graph to make it more simpler to understand. But we take these values where we check the hyperplane distance from each of the points, and ones with the average of the smallest margins would be the best hyperplane. So if you could look at here, oh, it's close to a couple of these, maybe it's really far from the reds. So we tilt it more towards the red. Yeah, so decision boundary, that's what this is called, is to separate the two classes to classify it. And you can definitely use this as a visualization if you're interested. Okay, cool. Now let's get into multi-class classification. So it's similar to binary classification. However, it's with 3 or more classes. So these would be mutually exclusive classes that you can classify. So one example is this picture over here. We have ducks and rabbits and all sorts of animals, and it would be able to classify all these animals into its appropriate categories. Another one would be motor imagery, so a cognitive process in which the subject imagines that the subject performs a movement without actually performing the movement, and it would tense the muscles. So being able to classify all the different movements that the person would be imagining would be another example of multi-class classification in a more physical, like humanly context. Okay, so let's go into one of the commonly used models. So this would be a decision tree. So you can see here, you start off with one and you keep splitting until you get to your different outcomes. And these are based on weights that you determine by feeding in data. So one example is a random forest, which it predicts by taking the average of the output from various trees. So it just takes a bunch of different trees, keeps averaging them to give you an outcome, something like this. And then we can go into another commonly used algorithm, which is called k-means, which aims to partition n observations into k clusters in which each observation belongs to the cluster with the nearest mean, serving as a prototype of the cluster. So in simpler words, you can see these different points here, and it's essentially grouping these points together to help you classify which one it would be. So you can see that they've made these little blobs, and if you get another new point that falls in here, you'll classify it as the green one, whatever that may be. And then we wanted to touch really quick on deep learning, which is a subset of machine learning, but it uses neural networks. So you can see these different like hidden layers that they have, and then you have an input and an output layer. So it's not exactly a model, but it is used pretty commonly in machine learning to make a lot of complex predictions. Yeah, so that's all for our machine learning video today. If you have any questions, please feel free to leave them in the comments down below and check out our other videos. Thank you so much for watching.